Let's talk about vertical freefall. Before we get into this, let me just define these couple of words here. When in physics we use the word freefall, what we mean is an object that's moving acted on by nothing but gravity. So freefall indicates that only gravity will be acting on the object. That means we'll be ignoring anything more complicated like drag, air resistance, wind, that kind of thing. If, for example, I take a baseball and throw it so that it goes flying through the air like this, while the ball is in motion, if I ignore all those complicated things, it's in free fall. Only gravity is acting on it. That's what we mean by free fall. Now, what we mean by vertical free fall is that instead of throwing the ball off at an angle like this, I'm only going to throw it straight up and down. So here we're going to be working in one dimension. Rather than throwing the ball off at an angle like that, what I'm going to do is throw it straight up in the air with some initial vertical component of velocity, and the ball is going to go straight up. It's going to reach some maximum height and it's going to come right back down. One-dimensional motion, vertical freefall. Now there's a long and interesting history behind people studying freefall, why and how fast things fall under the influence of gravity. I'm not going to go through all of that, but I encourage you to look it up and check out some of these interesting things. Probably it starts back with the Greeks and Aristotle around 350 or so BCE. And then the story winds up through the famous scientist Galileo at around 1600 AD. Galileo was the first person to convincingly demonstrate that acceleration was constant in free fall. And then in modern times, I encourage you to look up the astronaut David Scott, who famously, during Apollo 15 on the moon, dropped a hammer and a feather and showed that they fall together. On the moon, of course, there's almost no air resistance or drag, so things are in free fall. And that was in 1971, Apollo 15. So that was the astronaut David Scott. I encourage you to check out and read some more of that history. But like I said, Galileo was the first person to show that when an object is in free fall, its acceleration is constant. And it is directed straight down along the y direction. So AY is a constant, it's down, and it always has the same value that we call g, the acceleration due to gravity. When you measure this, it turns out that g equals 9.8 meters per second squared. So we have here two things about the acceleration. It's down, that's what this negative sign tells us. We'll take up to be our default positive direction. And it has a magnitude of 9.8 meters per second squared. So I can imagine as this ball is launched out of my hand, when the ball is moving up, the acceleration is down. It's always down. So the ball is going to be slowing down as it's going up, slowing down, slowing down, slowing down. At some point, the ball will reach its maximum height right here. And up there, Vy is 0. The ball is momentarily motionless. It's not moving when it's at the very top of its motion, but it's still accelerating. That's constant. It never changes. It's always minus g. So the velocity changes in the downward direction and the ball begins to move down, and it speeds up, speeds up, speeds up on its way down. Now, because the acceleration is constant, we can use the four kinematic equations that we developed last time. Let me write them for you over here. The first one was Vy is V naught y plus AYT. I wrote them for the x direction, but they work just as well for the y direction when AY is constant. Then we had delta y is half Vy plus V naught y t delta y is V naught y t plus half ay t squared. And the last one, the time-independent equation, Vy squared is V naught y squared plus 2ay delta y. Now these equations work for any vertical acceleration so long as it's constant, but in this case we know that ay equals minus g. So I can customize these equations for free fall by erasing ay, and everywhere I used to have an ay, I can put in its value, minus g. So this ay I'm going to get rid of, and I'm going to replace plus ay with minus g. I'm going to do the same thing everywhere else an ay appears. That ay is going to become minus g. This ay is going to become minus g. So let's put those in. Minus g, minus g. Okay, so there are the kinematic equations as they apply to free fall motion in one dimension. All right. Let's imagine now that we have this person who is going to throw this baseball up in the air. And we're going to calculate some things about its motion. Let's imagine that at t equals 0, the ball is launched from the person's hand. And it's launched upwards at a speed v naught y. It's going to go straight up into the air, and it's going to reach some maximum height we talked about, where it will stop momentarily, and then come back down. I want to calculate three things. I want to find t max, the time when the ball gets to this maximum height. I want to find h max, the maximum height that the ball rises to. Let me indicate that in this yellow color here. And let me find the time for the round trip to go up and back down again. I'll call that t sub r for time for the round trip. Okay, so those three things I would like to find. Let's first find the maximum time, how long it takes the ball to get up to its highest point. To do that, I can use the first kinematic equation. I have Vy equals V naught y minus gt. When the ball's at its maximum height, it's momentarily at rest. It's not moving, even though it's still accelerating. Ay is still minus g, but it's not moving. So Vy is 0. The final velocity there is 0. The initial velocity is what we launched it at, and we want to solve for the time. When it's at the top, that time is t max. So we find that t max is v naught y over g. Okay, that's how long it takes the ball to get up to its maximum height. And it scales as the launch speed. If you throw something 3 times as fast straight up, it'll take 3 times as long to get to the top of its motion. Let's find out how high it goes in terms of the launch speed and g. There's a couple of ways of finding how high it goes. Maybe the easiest is by using the fourth equation, which is time independent. So let's write it down. Vy squared is v naught y squared minus 2g delta y. Now again, starting from here and ending up here, the final y component of velocity is 0. It's momentarily at rest at the top. And delta y, the displacement from here to here, is now h max. So this becomes h max, and we can solve for it. How high does the ball go? It reaches a height v naught y squared over 2g. The maximum height that the ball reaches scales as the square of the launch speed. If you launch something 3 times as fast, it takes 3 times as long to get up to the top, but it goes 3 squared, 9 times as high. The maximum height scales as the square of the launch speed. Now let's find how long it takes the ball to go on the round trip, up and back down again. Probably the easiest equation to use for that is the third one. So let's take the third equation and solve it for t sub r, time for the round trip. So we have delta y is v naught y t minus 1/2 g t squared. Now for the round trip, the ball starts here, it goes up, and it comes back down. We're considering that whole motion. When it leaves the person's hand, goes up and comes back, and ends up back in the person's hand again, on the round trip, the displacement is 0. No displacement. Now I'm looking for the time when the ball gets back to that initial position, the time when it has no displacement. There are 2 times when it has 0 displacement. The first time is t equals 0, when the ball was first launched. The second time is when the ball gets back to the person's hand. That time is greater than 0, and I can find it by dividing this equation by t, so that t cancels that one, and I can solve for t sub g, time to get to the ground. That's going to equal 2v naught y over g. It's an interesting result. It took time v naught y over g to get to the top, and it took twice that long to get back to the original height. That means that however long the ball spent going up, it spent just as long coming back down. That's a consequence of a more general result we can see by looking at this last time-independent equation. Suppose we look at the ball at this height. There are 2 times when the ball is at this height, once when it's going up and once when it's going back down. Because they have the same displacement, they'll have the same speed. The square of the velocity will be the same. So if this is Vy here, that's going to be minus Vy there, but their squares are the same. For the same initial y component of velocity and the same displacement, they'll have the same square of the final y component. They'll have the same speed squared. Going up, it'll be positive. On the way back down, it'll be negative. And that's true at every height along the way. And that means that when you throw an object straight up in the air, the trip down is the mirror image of the trip up. At every given height, it's traveling the same speed, just in the opposite direction as it comes back down. Okay, so that's an introduction to vertical freefall. Let's look now at a couple of examples.